offers a range of services. Check your information panel after docking for more details. We would like to remind all commanders to avoid blocking access to docking.
Frameshift drive charging. 4, 3, 2, 1, engage. Frameshift drive charging. Frameshift drive charging.
Engage.
Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Fuel scoop disengaged. Frameshift drive charging. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Surface scanned by 50%. Surface scan complete. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Fuel scooping. Warning, temperature critical. Cannot comply. Frameshift drive charging. 4, 3, 2, 1. Engage. Warning, temperature critical. Fuel scooping. Fuel scoop disengaged. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Four, three, two, one, engage. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Four, three, two, one, engage. drive charging. System scan complete. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Four, three, two, one, engage. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Four, three, two, one, engage. Fuel scooping. Fuel scooping complete. Surface scanned by 50%. Surface scan complete.
Hello there, and welcome to the Sleepy Science Channel. If you're someone who likes to unwind by thinking about stars, planets, and the quiet beauty of space, you're in the right place. Tonight, we're leaving our solar system behind and drifting into the darkness between the stars, where other planets orbit distant suns and almost anything is possible. We'll visit worlds that rain metal, planets made of ice and fire, and lonely giants drifting through space with no star at all. Some of what you'll hear might sound impossible, but all of it is real. And if you enjoy these sleepy journeys, you're welcome to like and subscribe. It helps others find their way here too. But for now, get comfortable. Let your body rest. Let your thoughts wander. And let's begin. There are planets with temperatures hotter than stars. Stars are known for their incredible heat, glowing plasma furnaces burning millions of degrees. But believe it or not, some planets come close. One such world, Kelt 9b, reaches temperatures over 7,000 degrees Fahrenheit, hotter than many red dwarf stars. This gas giant orbits so close to its massive blue star that it completes a full orbit in just over a day. The planet is tidally locked, with one side facing the star permanently, absorbing a relentless barrage of radiation. Its atmosphere is being torn apart, streaming into space like a comet's tail. The heat is so intense that molecules break apart and metals can vaporize. It's not just hot, it's extreme beyond comparison. These ultra-hot Jupiters challenge what we thought planets could be. They blur the boundary between planet and star, blazing, storm-racked infernos that last only briefly before dissolving into the darkness. Some planets might be made almost entirely of diamond. It sounds like science fiction, but under the right conditions, it could be real. Some exoplanets, especially those rich in carbon, might form in ways that produce planets composed largely of diamond. If a planet forms around a star with more carbon than oxygen, the ingredients available during its birth can lead to carbon-rich structures. One candidate is 55 Cancri e, a super-Earth twice the size of Earth that may contain an enormous amount of carbon under intense pressure. That pressure, deep within the planet's interior, could create vast regions of crystalline diamond. It wouldn't glitter or sparkle the way we imagine. There would be no jewelry here, just darkness, heat, and unimaginable density. Still, the idea is captivating. A planet forged from carbon. A world where the mountains may shine with buried crystal. A place where geology becomes something almost otherworldly and precious. Some exoplanets orbit two suns, like Tatooine in Star Wars. In science fiction, we've long imagined twin sunsets, two stars sinking beneath a distant horizon. But now we know those strange skies might actually exist. Some exoplanets don't orbit a single star, like Earth does. they orbit too. These are called circumbinary planets, and they move in beautiful, complex loops around pairs of suns that orbit each other. When the stars are close together, a planet can circle them both as if they were one. If the stars are farther apart, the planet might orbit only one, tugged and tilted by the other's distant gravity. The result is a world with unusual light cycles, changing seasons, and double shadows. These systems are rare and delicate, but they do exist. So the sky of some distant world may truly glow with two dawns and two dusks, a sky once imagined in fiction, now quietly confirmed by science. There are planets where it rains molten glass. Some worlds are so alien that even their weather defies the imagination. Take HD 189,733b, a gas giant larger than Jupiter, orbiting so close to its star that it completes a full orbit in just over 2 days. The planet's atmosphere is scorching, with temperatures around 700 degrees Fahrenheit. Winds whip around it at thousands of miles per hour, and suspended in its blue, hazy skies are tiny particles of silicate, the building blocks of glass. When conditions are right, these particles condense and fall as rain. Not water, not ice, but molten glass, swept sideways by high-speed winds. From far away, this planet looks strangely Earth-like in color, a soft blue shimmer glowing near its sun. But up close, it's a storm-racked furnace, beautiful, violent, and utterly uninhabitable. It's one of many exoplanets that remind us nature's imagination reaches far beyond our own. Others may be covered in oceans thousands of miles deep. Some are exoplanets, ocean worlds, planets almost entirely covered in water. No continents, no islands, just endless global seas. These aren't like Earth's oceans, which only reach a few miles deep. On these worlds, the water layer could be hundreds or even thousands of miles thick. At the surface, it might be calm, windblown, or stormy. But deep beneath, the pressure would rise to incredible extremes, creating exotic forms of ice. Not the kind we know, but dense, high-pressure ice that forms under crushing weight. These planets may have rocky cores at their centers, hidden far beneath the water. Some may even have liquid layers warmed by internal heat. Could life exist in such oceans? We don't yet know. But ocean worlds may be more common than we thought. Gentle, glistening planets with no land, quietly turning in the dark, far from any sun we know. Some planets are tidally locked. One side always faces the star. Not all planets spin like Earth does. Some are tidally locked, meaning one side of the planet always faces its star, while the other remains in permanent darkness. The same thing happens with our moon. We only ever see one side. But imagine this on a planetary scale. One hemisphere scorched by unending daylight, while the other is trapped in eternal night. Between them lies a twilight zone, a ring around the planet where the light is always low, and the temperature might be just right. Some scientists believe that in certain cases, life could survive in this thin balance. These planets may be strange cloud formations and wild extremes in weather, but they're real, and they challenge our ideas of what makes a world habitable. Life, if it exists, might be in shadows, or just on the edge of the light. Hot Jupiters skim so close to their stars, their atmospheres boil off. Imagine a planet like Jupiter, massive, gaseous, and immense. Now move it far closer to its star. So close that a single orbit takes only days. So close that temperatures rise beyond 2,000 degrees. These are hot Jupiters, giant planets that skim just above their star's surface, so near that their upper atmospheres are literally being blown away into space.
Fuel scoop
We've discovered
disengaged.
many of these strange worlds, often among the first exoplanets we ever detected. Their sheer size and tight orbits make them easier to spot, but they're deeply mysterious. How did such massive planets get so close to their stars? Did they form there? Or were they pushed inward over time by gravitational forces? Some trail glowing tails of gas, like comets. Others are slowly shrinking as their atmospheres evaporate. They're unstable, dramatic, and often short-lived. Brief flashes of planetary fire, circling faraway suns. Some exoplanets are darker than chocolate. Some absorb nearly everything, becoming darker than paint, darker than ash, darker even than charcoal. One such world is TRES, a gas giant orbiting a star about 700 light-years away. Its atmosphere reflects less than 1%. Scientists aren't entirely sure why. It could be due to vaporized alkali metals or unknown chemical compounds in its upper layers. Whatever the cause, the result is extraordinary. A planet as dark as coal, glowing faintly with heat, nearly invisible in reflected starlight. Even its night side, already in darkness, is only slightly cooler than the day. If you could stand nearby and look toward it, you might see only the faintest silhouette against the fire of its star. A nearly perfect shadow, orbiting in silence,
Frameshift drive
absorbing the
charging.
light of the universe. We found planets floating alone, without a star. Most planets orbit stars, but not all. Some are wanderers, free-floating planets that drift through space alone, unbound by any sun. Known as rogue planets, and we've found evidence of dozens, maybe hundreds, across the galaxy. They might have formed normally, then been ejected from their home systems by gravitational disruption. Or they may have formed in isolation, like failed stars, never capturing enough mass to ignite. These worlds are dark, cold, and incredibly difficult to detect. But with powerful infrared telescopes, we can catch hints of their faint thermal glow.
Frameshift drive charging.
Some might still hold internal heat, keeping subsurface oceans warm for billions of years. Others could be completely frozen, drifting forever through the black. A planet without a sunrise. A world with no sunlight. Here, the quiet question persists. Could something live in such stillness? Some worlds may have ruby and sapphire clouds. When we think of clouds, we imagine water vapor, soft, pale, ever-shifting. But on some exoplanets, skies may shimmer with gems. On scorching hot gas giants, where temperatures soar above 2,000 degrees, minerals that would be rock on Earth can vaporize, rise into the atmosphere, and condense into clouds. Aluminum
Fuel
oxide,
scooping
iron,
complete.
titanium, and in some cases corundum, the mineral form of rubies and sapphires. These mineral clouds may scatter light in strange ways, tinting the skies red, purple, or deep blue. On one such planet, Pat P7b, researchers have seen shifting patterns in the atmosphere that suggest high-altitude mineral clouds sweeping across the sky. It's hard to picture a world wrapped in heat and storms, lit by a blazing sun, with clouds of liquid gems glinting and swirling overhead. The universe is stranger and more beautiful than we can easily imagine. There are super-Earths that could be more habitable than Earth. Some exoplanets fall into a category called super-Earths, rocky planets larger than Earth but smaller than Neptune. They may have stronger gravity, thicker atmospheres, and some of them may be even more hospitable to life than our own world. candidate is Kepler 442b, a rocky planet in the habitable zone of its star. Too cold. It receives just the right amount of sunlight and may have the mass needed to hold onto an atmosphere and liquid water. Some super-Earths could have deeper oceans, fewer tectonic disruptions, and greater surface stability, all conditions that might help life emerge and endure. Of course, we don't know yet if any of these planets are truly habitable, but they remind us of something humbling. Earth may not be the perfect planet, just the one we happen to call home. We've seen planets that orbit in just a few hours. Most planets take months or years to complete an orbit around their star. Earth takes 1 year. Mercury, the fastest planet in our solar system, takes 88 days. But some exoplanets move much, much faster. We've found worlds that orbit their stars in a matter of hours. One of the fastest is Kepler 78b, a planet just slightly larger than Earth, that completes a full orbit every 8.5 hours. It's so close to its star that its surface is likely covered in molten rock. Temperatures reach several thousand degrees. These ultra-short period planets are often tidally locked, their days and nights frozen in place. Their stars loom huge in the sky. Gravity pulls at their structure, and some may be slowly tearing apart. These planets are extreme, fast, hot, and fleeting. But they exist, skimming the edges of their stars like sparks flying from a flame. Other planets take centuries to complete one orbit. While some exoplanets race around their stars in mere hours, others take their time. Long, silent journeys that can last for centuries. One of the slowest moving planets we've found is GU Piscium b, a gas giant that takes about 1,000 years to orbit its star. Its orbit is so distant that it's barely held by gravity. If it were any farther, it might break free entirely. These long-period planets are incredibly hard to detect. We can't wait 1,000 years to watch them complete a loop. Instead, we catch them in motion, a curved path, a long arc, a hint of something vast. Some of these planets may have cold, dark surfaces, illuminated only faintly by starlight. Others may experience seasons that last lifetimes. On such worlds, change is measured not in years, but in generations, a slow and silent rhythm far beyond our own. We've discovered thousands of planets beyond our solar system. For most of human history, we only knew of one planetary system, our own. The sun, the moon, and the wandering stars that moved through the sky. But everything changed in the 1990 Z, when the first exoplanets were confirmed. Now, thanks to space telescopes like Kepler and TESS, we've found thousands. Planets around distant suns. Some small, rocky, and Earth-like. Others massive and strange. Some orbit tightly in just a few days. Others take centuries to complete a single trip around their star. Each discovery reshapes what we thought was possible. And still, this is just the beginning. We believe there are hundreds of billions of planets in our galaxy alone, more planets than stars. Worlds upon worlds, quietly orbiting in the dark. We'll never reach most of them, but we can listen for them, measure their shadows, and wonder what else might be waiting out there. We've detected planets using the shadows they cast during transits. The light from a star is usually steady, but sometimes, just briefly, it dims. A tiny dip, a momentary flicker. That dimming can mean a planet has passed in front of it. This is called the transit method, and it's one of the most powerful tools we have for finding exoplanets. When a planet crosses its star from our point of view, it casts a faint shadow, not in the dramatic way we see with eclipses, but in subtle drops in brightness, often less than 1%. Space telescopes like Kepler and TESS have used this technique to find thousands of exoplanets. From just those shadows, we can learn the planet's size, orbit, and even hints about its atmosphere. We're watching stars blink ever so slightly to learn about unseen worlds. The light of a distant sun interrupted by the quiet silhouette of a planet far away. Others were found by the gravitational wobble they induce. Even a planet's gravity can leave a fingerprint. When a planet orbits a star, it doesn't just move around the star, it causes the star to move slightly too. This wobble is tiny, but it's real. As the star shifts back and forth, its light shifts with it, squeezed and stretched by motion. Astronomers can detect those changes using spectroscopy, breaking starlight into its components and looking for the subtle signatures of motion. This is called the radial velocity method, and it was how the first exoplanets were discovered. It works best for massive planets close to their stars, like hot Jupiters, but it's also helped us find multi-planet systems and long-period orbits. We're not seeing the planets directly, we're watching their stars sway under their pull. Like a dance too distant to see, but close enough to feel in the music of the light. Some exoplanets appear to have atmospheres escaping into space. A planet's atmosphere is never truly still. Winds blow, clouds drift, particles escape. But in some extreme cases, the entire upper atmosphere may be drifting away, leaking into space like breath into the void. This is especially common in hot, close-in gas giants, where intense radiation from the nearby star can heat the outer layers until they reach escape velocity. These planets can develop long, comet-like tails of escaping hydrogen and helium. We've seen this in several exoplanets, where ultraviolet light reveals trails of gas streaming behind them. Some planets may lose significant mass this way over time. Others might be stripped down to rocky cores. This process helps shape the evolution of planetary systems, showing how stars can sculpt, reshape, or even destroy their planets. It's a reminder that even worlds can change, erode, and fade, leaving only their gravity behind. We've found planets in star systems with 3 or more suns. Not every star system is like ours. Some contain not 1, but 2 or 3 or even more stars orbiting together. And in a few of these complex systems, we've found planets. Imagine a world where the sky is never dark, where shadows stretch in different directions, where one sun rises while another sets. These planets must follow delicate, stable paths to survive the tangled pull of multiple stars. Some orbit closely around a pair of stars, circumbinary planets, while others orbit far beyond the entire cluster, tracing wide loops around a chaotic center. The lighting would be strange, the seasons unpredictable, and the sky full of motion. Yet these planets exist, and they remind us that planetary systems can form in ways we never expected. Even in places where gravity is complicated and the night sky never settles, planets find a way. Some worlds orbit the collapsed remains of dead stars. Stars don't live forever. Some end their lives as white dwarfs, small, dense remnants of stars like our sun. Others collapse into neutron stars, or even black holes. And around some of these stellar corpses, we've found planets. These worlds orbit what remains after a star has died, glowing embers or pulsing remnants of stellar fury. In some cases, they're survivors, somehow enduring the chaos of a supernova. In others, they may have formed from the debris left behind, rising from ashes into something new. The light from these stars is dim, cold, or distorted, but the planets remain, tracing silent paths through a kind of stellar graveyard. Some are blasted by radiation. Others drift quietly, circling dead suns in eternal twilight. It's haunting and beautiful. A reminder that even after the end, something new and strange may begin again. One planet orbits its star backwards. Most planets orbit in the same direction their star spins. That's how solar systems usually form, from a single swirling disk of gas and dust. But nature doesn't always follow the rules. We found at least one exoplanet, WASP 17b, that orbits its star in the opposite direction. Instead of moving with the star's rotation, it pushes against it. This backwards orbit likely formed through chaos, a near collision, a gravitational shove, or some violent rearrangement long ago. It's massive, bloated, and blisteringly hot, orbiting close to its star every few days. The fact that it moves in reverse challenges our understanding of how planetary systems evolve. And it proves something important. The universe is more flexible, more chaotic, and more surprising than any single theory. Some planets follow the flow, others push against it. And some, like this one, move through the cosmos with quiet defiance. We've seen signs of clouds on planets light years away. It may seem impossible, but we've detected signs of clouds on exoplanets dozens, even hundreds of light years away. Not by seeing them directly, but by studying the way starlight passes through a planet's atmosphere during transit. As light filters through the edge of an alien world, some wavelengths are absorbed, while others pass through or scatter, and this delicate fingerprint tickles suspended in the air. In several cases, the data suggest the presence of clouds. Not white, cottony clouds like on Earth, but dark, metallic, or mineral-based clouds made from silicates, iron, or exotic chemicals. These clouds might reflect or block starlight, shaping the planet's appearance and temperature. Some planets are permanently cloud-covered. Others show changing patterns across their skies. We can't yet see these worlds, but we can read their weather from starlight alone. Some exoplanets orbit closer to their stars than Mercury does. Mercury is already scorching, the closest planet to our Sun, bathed in light and stripped of atmosphere. But some exoplanets orbit much closer to their stars, at distances where no planet in our solar system could survive. These worlds complete orbits in mere hours or days. Their surfaces may be molten, their atmospheres whipped away by stellar winds. Some are tidally locked, with one side blistering in unending daylight, and the other frozen in eternal darkness. Others are so close they bulge from tidal forces, stretched like teardrops by their star's gravity. These extreme planets challenge our ideas of habitability, yet they're among the easiest to detect, thanks to their short orbital periods. Many of the first exoplanets discovered were in this category. They're hot, fast, and often unstable, but they show us just how flexible and extreme planetary systems can be. Others drift far beyond the reach of any sunlight. Not all planets huddle close to their stars. Some orbit so far away that sunlight becomes a faint and feeble glow. These distant worlds may take hundreds or even thousands of years to complete a single orbit. Temperatures plummet. Seasons span generations. And in the deepest cold, chemical reactions may slow to a crawl. Yet even here, planets persist, silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants, wrapped in frozen clouds. Others could be rocky and barren, crusted over with ice and carbon dust. And some may have hidden warmth beneath the surface, sustained by radioactive decay or ancient heat trapped from formation. These far-flung orbits are hard to detect, but their existence reminds us that planets can survive in places we once thought empty. Even in the loneliest reaches of space, a world can quietly endure. there are planets with spectacular hypothetical ring systems. Saturn's rings are beautiful, delicate bands of ice and dust, suspended around a gas giant. But they may not be the most impressive rings in the universe. Some exoplanets appear to have rings that are thousands of times larger, stretching across vast distances, wide enough to eclipse their closest stars.
Drive charging.
One candidate is J1407b, a giant planet or brown dwarf that may be surrounded by a ring system over 200 times larger than Saturn's. These rings could be made of ice, rock, or dust, possibly as the planet orbits, its rings may cast deep shadows on the star, creating strange dips in light that we can detect from Earth. If such a planet were placed in our solar system, rings would stretch across the night sky. They're hypothetical for now, but their shadowy presence hints at the grandeur still waiting to be confirmed. We've only just begun to scratch the surface.
Fuel
For all
scooping.
we've learned about exoplanets, we're still at the very beginning. The first confirmed discovery was made in 1992. In cosmic terms, that's barely a heartbeat ago. Since then, technology has leapt forward.
Fuel
Thousands
scooping
of planets have
complete.
been found, and thousands more await confirmation. We've detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. But we've barely begun to understand what these worlds are truly like. We can't yet see their surfaces. We don't know what they smell like, sound like, or feel like underfoot. We can't say which ones have clouds, continents, or creatures. The truth is, every new exoplanet we discover is a doorway to something we've never seen. And as our tools grow sharper, the picture will only grow stranger,
Drive charging.
richer, and more full of wonder. The cosmos is full of planets, and we've only just knocked on the door. Some planets orbit so close they slowly beam daylight. Because some exoplanets close to a star is more than just hot, it's destructive. These planets orbit so near their suns that the intense radiation and stellar winds begin to strip them apart. Layers of atmospheres heat up, expand, and gradually evaporate into space.
Fuel
Some
scooping.
form long, glowing tails of gas that stretch behind them, like comets caught in eternal retreat. Over time,
Fuel scooping
these
complete.
worlds lose mass, slowly shrinking, thinning, or transforming entirely. One planet, Kick 12,557,548b, may be crumbling under this kind of erosion, its surface shedding dust and debris with each orbit. It's like watching a planet dissolve in slow motion. These aren't just places to live, they're dynamic systems, constantly reshaped by their
Frameshift
environment.
drive charging.
Even something as vast as a planet can be worn away, little by little, by the unrelenting light of a star. We've discovered worlds that defy all expectations. Every time we think we understand planets, the universe hands us something. We've found planets where the skies shimmer with vaporized metal. We've found rocky worlds hotter than lava, and giant gas planets colder than deep space. We've seen worlds with tilted orbits, backward spins, and rings so large they could knock out a star. Some planets are too dense, others are too fluffy. Some shouldn't exist at all, at least not according to our models. But they do. Each strange discovery forces us to rethink how planets form, how they
Fuel
evolve,
scooping.
and what might be possible. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet
Fuel
contributions.
scooping complete.
Little cosmic puzzles scattered through space, waiting for someone to notice them and wonder. Some exoplanets might be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, just endless oceans. stretching in every direction. These are water worlds, exoplanets, where the surface may be completely covered by liquid water. Not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would be intense, enough to compress water into exotic ices and crush rock into unfamiliar forms. Some of these worlds might have atmospheres rich in steam or clouds of vapor circling overhead. Others could be wrapped in hazy mists, warmed by sunlight and turned. If life exists on these planets, it falls in a deep, sunless sea, shaped by currents and chemistry rather than light. We haven't confirmed one yet, but the evidence is growing. And if Earth is one kind of habitable world, perhaps these dark oceans are another kind entirely. We've found mini Neptunes, small but swollen with gas. Not every planet falls neatly into the categories we know. Between Earth and Neptune lies a curious group of worlds called mini Neptunes. They're bigger than Earth, but smaller than our ice giants, and many are wrapped in thick layers of gas. These planets likely have rocky or icy cores, surrounded by envelopes of hydrogen, helium, and other gases. They may look similar to Neptune from a distance, but inside, they could be wildly different. Some have deep, boiling oceans. Others might have no solid surface at all. They're too small to be true gas giants, but too big to be rocky super-Earths. For a long time, we didn't even know if planets like this exist. Now we know they're common, possibly the most common type of planet in the galaxy. Strange, swollen, and still mysterious, they fill in the space between what we expected. Some planets are puffed up like balloons. Some exoplanets are so inflated, they seem lighter than they should be. These puffy planets are large in size but low in density, huge soft worlds that could float in water if they were somehow dropped into a bathtub the size of a star. One example is WASP-17b, a gas giant twice the size of Jupiter but with only a fraction of its mass. These planets likely formed far from their stars, then migrated inward. Now, intense heat from the star causes their atmospheres to swell and expand. Radiation from the star may be breaking apart molecules, adding to the planet's strange properties. Some puffy planets are others seem impossibly light for their size. We still don't fully understand them, but they show how elastic a planet can be. Not rigid and fixed, but soft, unstable, and stretched by light. There are exoplanets with days longer than their years.
Fuel scooping.
On Earth, one day and 1 year are very different things. We spin on our axis once every 24 hours, but it takes 365 days to orbit the Sun. Not so for some exoplanets. In certain cases, especially for planets orbiting very close to their stars, the time it takes to rotate is longer than the time it takes to complete an orbit. That means the planet completes a full loop around its star before it even finishes turning once. These planets are usually tidally locked, with one side permanently facing their sun. The night side remains in darkness, frozen and still, while the day side burns under endless daylight. There's no sunrise or sunset, just one eternal face to the light. On such a world, the idea of time itself begins to blur. A day that never ends. A year that races by. A sky divided into hazy skies. We often imagine alien worlds with clear skies and stunning views. But some exoplanets might be wrapped in thick layers of haze, blocking light and obscuring it. These hazes can be made of complex hydrocarbons, photochemical smoke, or exotic clouds of unfamiliar chemistry. On Earth, we see this kind of effect in places like Saturn's moon Titan, where a golden fog hides the surface from view. On exoplanets, especially
Fuel
those
scooping
orbiting
complete.
cooler stars, ultraviolet light can trigger strange reactions in the upper atmosphere, building up thick, murky layers that trap heat and scatter light. These planets may look dull or muted from space, their colors softened by haze. But beneath the clouds, oceans might churn, winds might scream, and alien landscapes may wait in silence. We can't see them clearly, not yet, but we know the haze is there, a veil drawn over distant, hidden worlds. We've seen evidence of winds whipping at thousands of miles per hour. Weather doesn't just happen on Earth. On many exoplanets, especially large gas giants, atmospheric winds can reach extraordinary speeds, far beyond anything seen in our solar system. Some exoplanets are tidally locked, with one side always facing their star. That intense, permanent heat creates powerful thermal gradients that drive fierce winds around the planet's atmosphere. Using space telescopes, astronomers have detected signs of winds blowing at up to 5,000 miles per hour, fast enough to travel the width of the United States in under an hour. These winds can shift clouds, reshape heat patterns, and carry vaporized metals across the planet. Some even redistribute light itself, shifting the brightest part of the planet away from where the star's light hits directly. It's invisible to the eye, but written into the glow of the planet's light, a whisper of motion in a faraway sky. Some planets could be tidally heated from the inside. Not all heat comes from a star. Some exoplanets, especially those in eccentric orbits, may be heated from the inside out, thanks to tidal forces. As they move through varying gravitational pulls, their interiors stretch and flex, creating friction and warmth deep below the surface. This is how Jupiter's moon Io stays volcanically active. And it may be happening on exoplanets too. Planets orbiting close to large stars or courting gravitational dances with neighboring planets can experience this kind of tidal heating. In some cases, it could melt rock into magma or keep subsurface oceans liquid beneath thick shells of ice. These planets might look cold or dark on the outside, but inside they're alive with motion. Heat without sunlight. Activity without a star. It's a reminder that energy can come from within, and that even in the outer reaches of a system, a planet may still be warm. We've discovered planets in ancient star systems. Some stars are nearly as old as the universe itself, formed in the galaxy's earliest chapters. And around a few of these ancient stars, we've found planets. They've been orbiting for billions of years, far longer than Earth has existed. One example is Kepler 444, a star system over 11 billion years old, with 5 small rocky planets. These worlds are from a time when the universe had fewer heavy elements, suggesting they may have formed from different materials than Earth. What might such planets be like? Could they be worn smooth by eons of impacts? Could they have once supported life, long before life began here? We may never know. But these ancient systems remind us how long planets can last, surviving stellar storms, galactic tides, and the slow march of time. They are cosmic elders, quietly circling in the deep past, still here, still turning. Some exoplanets may have moons we've yet to find. Where there are planets, there may also be moons. And yet, for all the exoplanets we've discovered, exomoons, moons orbiting planets outside our solar system, remain elusive. They're hard to detect, small, subtle, often hidden in the noise. But we've seen hints. Tiny variations in a planet's transit, wobbles in timing, dips in brightness that don't quite match the model. One candidate, a possible moon orbiting the gas giant Kepler 1625b is still under study. If confirmed, it would be huge, larger than any moon in our solar system. But even smaller exomoons could be important. They might stabilize planetary climates, shape tides, or even provide sheltered environments for life. Some moons could have subsurface oceans, like Europa or Enceladus. Others might be rocky and cratered, drifting in twilight above gas giants. We haven't seen them clearly yet, but they're likely out there, circling in the quiet, waiting to be found. Others have entire moon systems of their own. Just as planets orbit stars, moons orbit planets, and for massive exoplanets, especially gas giants, it's likely they have entire systems of moons. In our solar system, Jupiter and Saturn each have over 80 moons, ranging from tiny captured asteroids to massive worlds with subsurface oceans. Now imagine a gas giant, many times more massive than Jupiter, orbiting a distant star. It could have dozens, perhaps hundreds of moons, a miniature solar system all its own. Some moons might be rocky and cratered. Others could have icy shells or thick atmospheres. A few might even orbit in the habitable zone of their parent planet, shielded from stellar radiation and warmed by tidal forces. We haven't confirmed any of these exomoon systems yet, but the potential is staggering. Not just planets, but whole families of worlds, drifting together, locked in gravitational harmony, far from home. Some exoplanets might support life, but not as we know it. When we imagine alien planets, we picture Earth-like conditions, blue skies, liquid water, and a comfortable temperature range. But life might not need any of those things. Some exoplanets could have environments wildly different from our own, in acidic clouds, beneath ice-covered oceans, or in high-pressure atmospheres thick with oil. Even life that doesn't rely on water, or coal, or DNA. Extremophiles on Earth already live in boiling acid pools, radioactive caves, and near volcanic vents with no sunlight. So, on distant planets, it's possible that life could take stranger forms. Not walking, talking creatures, but microbial networks, chemical colonies, or self-replicating systems that thrive in environments we would find deadly. We may never meet them. But if we listen closely, in the light and shadow of alien worlds, we might someday find the first faint signature, a chemical imbalance, a breath of something living. We've found planets that barely skim the edge of being stars. There's a line between planet and star, and some exoplanets sit right at the edge. These are giant objects called brown dwarfs, or super-Jupiters. They're massive enough to fuse a little deuterium in their cores, but not enough to sustain the fusion reactions that power real stars. They glow faintly with leftover heat from their formation, and some may even emit infrared radiation. One such object, Colonia 2546b, is so large and hot, it may straddle the boundary between planet and failed star. We're still debating where the cutoff lies. How massive can a planet be before it becomes something else entirely? These in-between worlds, planets, or like stars. We don't always know which, but they remind us that categories in space are often blurry. The cosmos is full of edges that shimmer and shift, where one thing slowly becomes another. Some worlds lie right on the edge of the habitable zone. The habitable zone is often called the Goldilocks zone, the range around a star where temperatures are just right for liquid water. But many exoplanets lie right at the edge of this zone, where conditions are more uncertain. Too far out, and water freezes. Too close in, and it boils away. But on the boundary, things become more complex. A thick atmosphere might trap heat. A high reflectivity might keep a planet cool. And seasonal shifts or orbital eccentricity could cause dramatic climate swings. One hemisphere might be habitable while the other remains too cold or too hot. Life could exist only in pockets, beneath the ice, in deep caves, or around volcanic vents. These edge worlds are neither fully comfortable nor completely barren. They're places of tension and potential, where the balance between warmth and cold, light and dark, could tip either way or hold, just barely. We're learning to study the chemistry of alien atmospheres. Until recently, the idea of analyzing the atmosphere of a planet light years away seemed impossible. But now, thanks to precise instruments like the James Webb Space Telescope, we're starting to do exactly that. When an exoplanet passes in front of its star, some of the starlight filters through the planet's atmosphere. That light carries subtle fingerprints, spectral lines, from the molecules in the air. By breaking the light apart and analyzing those lines, scientists can detect water vapor, carbon dioxide, methane, and more. We can begin to guess at clouds, pressure, and even temperature. In some cases, we may even spot biosignatures, chemical hints that life might be affecting the atmosphere.
Fuel scooping complete.
It's like reading a message from across the galaxy, hidden in the colors of starlight. We're still early in this work, but with each new spectrum, we get a little closer to understanding what alien skies are truly made
Frameshift
of.
drive charging.
Some exoplanets may have seasons that last for decades. On Earth, our seasons are defined by a tilt, a gentle lean that changes the angle of sunlight across the year. But on some exoplanets, a larger tilt, a stretched orbit, or multiple stars can create wild seasonal effects, with summers that last for decades and winters that span entire lifetimes. A planet close to its star, warming dramatically, then drift away into a deep, frozen hibernation.
Fuel
Others might
scooping.
have chaotic seasons, shifting unpredictably with every orbit. Long summers could allow life to bloom, only to vanish
Fuel
beneath
scooping
decades of
complete.
cold. Or entire generations might live and die within a single spring. The rhythm of life, if it exists, would follow a different kind of calendar, written not in days or years, but in slow arcs and stellar dances. On these worlds, time moves differently, and so might everything else. Others might experience eternal twilight. Some exoplanets may live forever in the in-between, a place where day never fully breaks and night never completely falls. This can happen on tidally locked planets, where one side always faces the star and the other never does. But between these extremes lies a thin region called the Terminator, a ring of perpetual twilight. Here, the sky might glow dimly forever, caught between burning light and endless dark. The temperature could be more stable, the winds more moderate. If life exists, it might flourish along this twilight boundary, a narrow band of gentle shadows and muted warmth. There would be no sunrise, no sunset, just the soft, slanted glow of a star locked at the edge of the sky. A planet with a horizon that never moves. A place where time drifts in half-light and nothing ever truly sleeps. We've discovered planets locked in orbital resonance with each other. In some star systems, planets don't just orbit independently, they move together in quiet synchrony.
Frameshift
These are
drive
called
charging.
orbital resonances, where the timing of their orbits aligns in whole number ratios. For every 2 orbits one planet makes, another completes exactly 3. This balance keeps them from colliding and helps stabilize their motion. Our own solar system, among Jupiter's moons, for example. But we've also found exoplanetary systems with long chains of resonance involving 3, 4, or even more planets. cosmic symphony, with each world playing its own rhythm, separate, but always in harmony. These arrangements are delicate.
Fuel scooping.
A small change in gravity or motion could throw everything off. But instead, they hold it gently.
Fuel scooping complete.
Orbit after orbit. The universe, it seems, is not just chaotic, it's also deeply musical. Some planets show mysterious signals we still don't fully understand. Not everything we observe makes sense right away. Some exoplanets show light curves that fluctuate unexpectedly, dimming and brightening in ways that don't match simple models. Others appear to have rings or clouds or orbiting debris that cast irregular shadows. One star, nicknamed Tabby's star, dimmed in strange, uneven patterns that sparked global curiosity. Some thought it might be a swarm of comets. Others imagined vast artificial structures, though no evidence supports that idea. Still, the mystery remains. Light curves wiggle and wobble. Transit patterns shift. Some planets show extra dips in brightness before or after they pass in front of their stars. Others change shape, as if wrapped in clouds or trailing dust. We're beginning to decode these patterns. But for now, they remain unanswered questions, gentle flickers of something we don't yet understand, but can't look away from. There are planets with orbits so wild they nearly escape their stars. Most planets move in quiet, regular loops. But some exoplanets follow long, stretched-out orbits, so elongated that they swing far from their stars before plunging back in, like cosmic comets. These orbits can last hundreds of years. At their farthest point, the planet may receive almost no light or warmth. At their closest, they race past their star, pulled by intense gravity, heated in brief, blinding flashes. These journeys are violent, unstable, and often temporary. Some planets may have been flung into these orbits by collisions or by passing stars. Others may one day be lost entirely, escaping their systems to drift alone in interstellar space. They are cosmic exiles, barely bound, dancing on the edge of gravity's grip. Their paths are unpredictable, their futures uncertain, but still, they orbit, each pass a reminder of how dynamic and dramatic the life of a planet can be. Some exoplanets orbit burnt-out stellar corpses called white dwarfs. After a star like our Sun dies, it leaves behind a white dwarf, a small, dense ember of what it once was. These stars no longer fuse hydrogen. They don't shine with the energy of youth, but they remain hot and bright for billions of years. And around some of these stellar remnants, we've found planets. Some are close in, surviving unimaginable changes as their star ballooned into a red giant and collapsed. Others may have formed later from leftover debris. The environment is extreme. Radiation can be intense. The gravity near the white dwarf is crushing. But even here, planets persist. Some may even lie within the narrow band where temperatures are right for liquid water. These planets orbit the dead, but they're not dead themselves. They're survivors. Echoes. Proof that even in the aftermath of stellar death, the story of planets may go on. Others may have formed from the remains of destroyed worlds. In the chaos of a young solar system, collisions are common. Planets can be shattered, moons torn apart, and debris scattered across space. Sometimes from this wreckage, new worlds form, built from the remnants of earlier ones. We've seen hints of this in the dusty disks around some stars, where ring-shaped gaps suggest collisions or ongoing construction. Some exoplanets may be the cause of once larger planets, stripped of their atmospheres. Others might be aggregates, assembled from fragments, fused by gravity and time. These are recycled worlds, not born whole, but rebuilt from the pieces of something else. Their surfaces may be rough, scarred, or molten. Their orbits may be tilted or eccentric, but they exist, and they remind us that destruction isn't always the end. Sometimes it's just the start of something new, stranger, rougher, and more resilient than before. There are planets that may have once been part of another star system. Planets form around stars, that much we know. But over the long life of a galaxy, stars and their planets don't always stay together. Gravitational encounters, close flybys, or chaotic cluster dynamics can fling planets from one star system into another. Some exoplanets may have started their lives orbiting one star and ended up captured by a different one. These interstellar adoptees can end up on odd orbits, tilted, elliptical, or unstable. We can't always trace their origin, but in some cases, their chemical signatures or motions hint that they don't quite belong. They're cosmic immigrants, pulled from one family into another, survivors of stellar drift and gravitational chance. And they remind us that solar systems aren't sealed, they evolve, trade paths, and sometimes gather strangers from the stars. Some exoplanets could be young versions of what Earth once was. When we look at distant planets, we're not just seeing other worlds. Sometimes we're seeing different versions of our own past. Some exoplanets may resemble early Earth billions of years ago, when the atmosphere was thick with carbon dioxide or methane, and life, if it existed, was just beginning to take hold. These young planets might still be forming continents, building atmospheres, or undergoing massive geological change. Volcanic activity chemical reactions, and extreme weather could shape their futures.
Frameshift drive charging. Ready to engage. Frameshift drive charging. Four, three, two, one, engage. System scan complete. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Four, three, two, one, engage. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. drive charging. Fuel scooping. Fuel scooping complete. Frameshift 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 drive charging. Frameshift drive charging. System scan complete. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. Fuel scooping. System scan complete. Fuel scoop disengaged. Frameshift drive charging. 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 charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Ready to engage. Four, three, two, Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping. System scan complete. Fuel scooping complete. Frameshift drive charging. Fuel scoop disengaged. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Ready to engage. 3, 2, 1, engage. Fuel scooping. Fuel scooping complete.
Papa India Lima. Thank you for choosing our station, Commander. We hope you find everything to your liking. Access granted. Please head directly for Bay 07.
Copy that. Clearing a flight path for departure.
Reports of increased traffic surrounding the facility. Regulate your speed, Commander.
Landing gear deployed.
dispatched. Greetings, Commander.
Facility officer range. Security.